Okay, hello again, everybody. Welcome to the second installment. We will start talking about math again, and in particular, apportionment. So, for those of you who weren't in class last Thursday, I started talking about this, but not very much. I kind of did some fun things. I looked at some pictures, including this one, which I've scanned in from a book, and I'll upload. And I'll go back to this pictures again, but it outlines the different methods we've used for apportionment in the history of American politics. So I'll bring that up, and in particular, we will focus on two methods: Hamilton's method, which my book writes down as the greatest fractions method, and the Huntington Hill method. But these will be coming later. This video will just be some basics of apportionment. What is it? What are we talking about? What vocabulary do we need to know, etc. So, let's start off. Chapter 4, Apportionment. So, the way I think about apportionment, or I've been thinking about it, given the way our book presents things, you can think about this much like the weighted voting equivalent of the fair division games. So apportionment is not so different than the fair division games that we were playing before. You have a set of objects and a set of parties, and you're trying to divide up those objects fairly between the parties. Now the difference here is that in Chapter 3, each party had the same weight. They were just people that we were trying to divide things between. But here in Chapter 4, apportionment deals with the dividing up of objects between parties which don't necessarily have equal weight. So the example that we will come back to over and over again will be our own political system. So the House of Representatives is a good example of apportionment. The way this works is that the House of Representatives has a fixed number of seats. That has changed over the course of history, but at the moment there are 425 seats in our House of Representatives. And there are 50 states in the country, plus some other territories or the District of Columbia, etc., that we consider as states in this apportionment process. Now, the weights that I'm talking about correspond to the populations of each state. A bigger state has a bigger population, that should be given more seats than a state with a smaller population or a smaller weight. So, can think of this as weighted fair division. Because, if you want to give a definition of apportionment, I'll get to a definition of apportionment. I could give it. Why don't I give it here? So, an apportionment method is a division of m objects. Why don't I just say a finite number of objects? We'll call these objects seats. Amongst a finite number of parties. We'll call these parties states. A division of a finite number of objects amongst a finite number of parties based on population. Or the weight of each. state. Okay. So, I'll just get started writing down some vocabulary terms. I'll define what a seat is, what a state is, what a population is, though those things are relatively self-explanatory. I should mention that apportionment doesn't just refer to seats in a House of Representatives to being divided amongst states in a country. It's not always like this. You could be apportioning nurses to different wings of a hospital. Say you had 20 nurses, this will be a homework problem. Say you had 20 nurses and 3 wings of a hospital, and each wing has a different number of beds, so it wouldn't make sense to send an equal number of nurses to each wing of the hospital. You couldn't divide 20 by 3 anyway, but you would want to divide them proportionally. So this is very much about proportions. Okay. Good. So it requires 2 parts. So this requires 2 parts. The first is the dividing. That is the dividing up of seats amongst the states. And the second part is that this is done proportionally. Okay, so like I say, this could apply to anything from sharing candy to seats in legislature. Okay, so some vocab. Let's get that going. Some vocab. Okay, so the states. We're going to have N states in general. We're going to let the capital letter N denote the number of states. These are the N parties having a stake in the apportionment. Okay. These don't have to be normal states. They could be countries, you know, in a global apportionment, if that were to happen. So we will also have the seats. These are going to be the M, capital M and capital N, discrete objects. And if you remember, we talked about this word discrete. It's very important in our finite math class. It pops up over and over again. These are discrete, means indivisible. These are objects that you can't divide in half. Can't give half a seat in the House of Representatives to a state, because that seat corresponds to a person, and that you can't have half a person. Good. The M discrete objects to be divided up. Indivisible. Are to be divided amongst the states. Okay. So again, just to reiterate, this is to say that every state has to get an whole number of seats because they're indivisible objects. So every state receives a whole number of seats. Okay. In general, we'll deal with situations where there are more seats than states. For our, political purposes, it doesn't make much sense to talk about situations where there would be more states than seats. In this case, you would have states without any representation in the House, and that would defeat the whole purpose of the House of Representatives. So yes, in general, we will consider cases in which cases with more seats than states. Okay, so I hope that's clear. The third pretty intuitive vocabulary word we'll be using is population. These are, in essence, the weights corresponding to each state, but we'll word it a little different than that. To each state corresponds a positive whole number. So the weight in our voting systems was the number of votes you control. That was also a positive whole number. This population is still a different example of a weight. So a positive whole number, which is used as a basis for the apportionment of seats. Okay. We'll talk about population in two senses. The total population being the population of the country, and population of each state. We'll use a capital P to represent the population of the whole country, and we'll use a lowercase p to represent the population of each state. So that's the total population. P is the sum of the populations. Oops, that's not how you spell. Populations of each state. And those will be represented by a little p sub I. So, i.e., P is equal to P1 plus P2 plus all the way up to Pn, where P1 through Pn are the populations of states 1 through n. Capital N, that is. Okay. And I guess I just I defined what apportionment was up here, a division of the finite number of seats, but now I'll say an apportionment method. An apportionment method is a systematic procedure that guarantees a division of the m seats to the n states using some formula. So it's not just good enough that this method works in some cases. We want it to guarantee, we want to have a formula which is based on population, which guarantees that every time we use it on no matter what population, what country we're using it on, we can divide the m seats up between the n states fairly, in quotation marks. So a systematic procedure which guarantees a division of the gotta remember m or n, m seats amongst the n states using some formula based on population. Good. So that guarantee is very important. And in order to do this, we'll need some more terminology. So the vocab lesson continues. This is not a simple thing to do. It might seem like it should be, but well, rounding has its problems. We'll see. We'll do some examples soon once I get the rest of this vocabulary out of the way. So, in order to study these methods, we need a few more terms. This will be much more mathematical terms. Let me zoom out a little bit. Good. So, I won't do numbers. So, the standard divisor is going to be the ratio of the total population to the number of seats to be given away. So, the standard divisor is the ratio So what does that mean? In math terms, that looks like SD, that's going to be our standard divisor, is going to be the total population, which remember we represent with a capital P, over the number of seats, which is capital M. What does this mean for us? Well, the standard divisor is exactly the number of people which correspond to one seat. So if you take the total population in the country, divide that by the number of seats, you should get the number of people which correspond to a single seat. Okay, so related to the standard divisor now that we have this, this is just going to be a number, and it's going to, every country, every collection of states is going to have some standard divisor. But now we have one standard divisor, but each state is going to have what we call a standard quota. This is going to be, okay, so given that this number of people correspond to a single state, now, a single seat, now if my population has, if my state has this many people in it, how many seats should I get? That's in essence the question we're asking. So, the standard quota of a state is the exact fractional number of seats a state would get if fractional seats were allowed. So remember what I was saying before. We're trying to divvy up a whole number of seats to each state. We don't want any state to have 4.5 seats because we don't know what to do with that half. And so the standard quota is, sometimes the number of seats will divide evenly into your population. If your total population is 20 people in our class and we had 5 seats to give away, Well, your standard divisor would be 4 seats, 4 people corresponding to each seat. Now, if our class was divided up into 2 states, and one state had 8 people and the other had 12, well, then your standard quota, just taking each state's population and dividing it by the standard divisor, would give you a whole number. So a standard quota can be a whole number, and that's all good. But most of the time it isn't going to be a whole number. This is because our populations will often be very big in the examples we're talking about, and the number of seats might be big too, and so then it just gets very unlikely that that they will divide each other evenly. So the standard quota is helpful to know. It tells you how many seats a state thinks it should get, but it's not necessarily realistic, because in reality we have to either round that number down or round it up to give them a whole number of seats. Good. So let's represent that standard quota mathematically like we did the standard divisor. So here the standard quota is going to be represented by a little q sub I for state I is going to be the population of that state divided by the standard divisor. So maybe I should have written this. If fractional seats were allowed, these quotas are denoted Q1, Q2 through Qn for states 1, 2 through n. And remember, this doesn't mean that we have more than 2 states. It's just saying that for each state, the standard quota, Q sub I, so Q1 is the population of state 1 divided by the standard divisor, which is the same for every state. Q2 is the population of state 2 divided by the standard divisor, etc. Like I say, these are almost never whole numbers. Whole numbers. And so in practice we need 2 different quotas. Sorry. So the 2 different quotas we're going to talk about are the lower quota and the upper quota. And these are exactly what you might think. The lower quota is simply the standard quota rounded down. And the upper quota is the standard quota rounded up. Now remember that these quotas correspond to a specific state, while the standard divisor corresponds to the whole system. It's good to keep in mind. Okay, so there we have all of the basics. And so now that we have our vocabulary here, I think it's time that we did an example. So I'm taking an example from the book. They've made up a fictional country named Parador. I don't know where Parador is. Well, I just said it's fictional. But I don't know where they came up with that name. But let's go with it. So, a fictional example. But just to get you all really, well, to motivate these definitions, to give you something to put a picture behind these words. Good. So, a country named Parador has 6 states. The book gives them names, but I'm just going to call them A, B, C, D, E, and F. The state end, I will list their populations in a little table here, along with the total population of Peridor, which is 12,500,000. Okay, so state. Well, let me make a little table. So I'll do state A, B, C, D, E, F, and here I'll make a little line for total. And I will, okay. Good. I'll get rid of this little line and try and make a nice straight line. Okay. And on the next line, I will write their populations. So the population of the first state is 1,646,000. Next one is 6,936. You know what? I'm just going to, nah, I won't. 6,936. $154,000, so state C is a small one. 2,091,000. Here, state E has 685,000, and state F has 988. Okay, and so the total population of Peridor is 12,500,000. Your book added all those things up. I did not. But we will do some math on them anyway. I know they're big numbers, but we'll deal with it. So, the first thing so now that we have our populations, our states, what other information do we need to know? Well, we have our states, we have our population. We need to know how many seats we want to divide up between the states if we want to do any apportionment here. So, why don't we say that your book says, actually, that there are, why don't I start it down here? Yeah. There are 250 seats. Oops. In total. Now, the question is, how do we divide up these seats between each state? Their populations clearly vary significantly, so if we want to give away all 250 seats to the states, how many should each state get? Well, let's calculate the standard divisor, shall we? So, first step, standard divisor, SD, is equal to what? Well, we said that the standard divisor is the total population over the number of seats. Okay? We take the total population. Why don't I write that really quick? Total population over number of seats. And that's going to be 12,500,000 divided by 250. And so, let me type this into my calculator here. We should get 50,000. Okay, so what does this mean? This means that every 50,000 people that a state has, they should get 1 seat. So, for every 50,000 people, that state should get a seat. Okay. So, what does that mean? Well, let's find out their standard quotas. Okay. Well, when we wanted to find the standard quota, I said that the standard quota Q sub I is equal to the population of that state divided by the standard divisor. So let's see what happens. State A. So why don't we calculate Q sub A? Well, that's going to be the population of state A divided by the standard divisor. So what's the population of state A? 1,646,000. 646,000 divided by the standard divisor, which we just calculated to be 50,000. And what do we get then? 1,646,000 divided by 50,000. This gives us 32.92. So what does this mean? This means that if we could split up the state seats in half or in thirds or in 0.92s, then state A should get should get exactly 32.92 seats. But since that's not possible, we want state A to get pretty close to 32.92 seats, right? So already, hint, hint, rounding is going to be an important lesson to learn soon. So quota for state A is 32.92. We could, so let's enter that in to our little table. We could do it for state B, and then because your book has already calculated these, I won't do all the rest. But what was population of state B? Well, that was 6,936,000. I will copy that. So now the quota for state B is going to be the population of state B divided by the standard divisor, which is going to be C. Paste that, make it a bit bigger so you can see what I wrote. And I'm going to divide that by 50,000 again, because remember, the standard divisor doesn't change. Once you calculate it once, you're done. Okay, and so what's this going to give us? This is going to give us 138.72. And so again, this is the exact number of seats that a state should get if we could divide those seats up into fractions. What you'll notice now, 138.72. Let me enter that in here. 138.72. Now you'll notice that this looks right. So state B had maybe 4 times the population of state A. And so their standard quota should be roughly 4 times as big, and indeed it is. So that's how these things play together. And I'll write down the other standard quotas because I have them here in front of me. 3 came out to 3.08. D came out to 41.82. E came out to 13.70. F came out to 19.76. And so if we sum all of these up, what should we get? Well, beautiful. 250 seats. So good. They all add up. So if we could split them up, this is the apportionment method. This is it. Wouldn't that be nice if we were just done there and we could just do some basic division and say it was finished? But no such luck. Because we have to give every state a whole number of seats. Now let's just take a look at this table. This table right here. I won't mess with it anymore. So how are we going to give everybody a whole number? Seems like the obvious answer is to just round every number, right? So let's see what happens when we just round every number. Well, we could round state A's number to 33. It's definitely pretty close to 33. Round state B should get rounded up as well because 0.72 is bigger than 0.5. So let's say 139. And C is pretty close to 3, so let's round that down to 3. Let's round D up to 42. So this one goes to 14, and this one goes to 20. This is just basic rounding. But let's see what happens when we add all of these up. 33 and 139 makes 172, and 3 makes 175, and 20 makes 195, and 42 makes 237, and 14 makes, oh dear, that makes 251. Now that's not all right. We don't have 251 seats to give away. We only have 250. So this really, I guess, goes to show that we can't just round everything as simply as we thought we might be able to. So this means that basic rounding is not an apportionment method. Because we found a counterexample. Remember, sometimes basic rounding will work. You know, is the only reason that rounding didn't work here is that we rounded 1, 2, 3, 4, 5 of these numbers up, and only one of them got rounded down. And so because we kept rounding everything up, we ended up with one more seat than we have to give away. But if a couple of these had been lower and we had rounded an even number of them down and an even number of them up, then maybe this would have worked. But just the fact that we found one which doesn't work, and remember, an apportionment method is supposed to guarantee a division of the m seats amongst the n states. This doesn't do it. So, basic rounding doesn't work. But what does? And I will let you ponder that question. Maybe you could come up with an idea for apportioning these seats. Think about it. What other method might you use to make sure that everybody gets a whole number of seats, which is close to their standard quota, but make sure that they always add up to 250? I will answer that question in the next installment. So, tune in to section 4.2 next episode.